All right. Hi, happy Tuesday. Thank you for coming. Um, so we're continuing our tour of different algorithms. So today we're looking at planarity. Thursday, we'll look at vertex coloring. And then the this is week 13, I think, something like that. Then we'll have some days to look at hard problems. So like NP-complete problems and try and see what we can say about them. And just so you have experience looking at these and being able to recognize them. And vertex coloring is one of those, but we'll maybe spend a little bit more time on that. In terms of assignments, keep working on your project. I went through and I graded the progress reports. So if I left you comments, make sure you look at that. Yeah, I think there's another due this week. I have many things to grade. But keep in mind the minimum spanning tree stuff is due tonight. We have an activity today in class, which is just due Thursday, but you should be able to do it today. And then the week 13 progress report is due on Friday. So make sure you're making progress and start preparing for the presentations. So we'll have time on that last week of class to do presentations. All right, so I've added a new PowerPoint here. It's called Planarity Coloring because I think I'll put the coloring stuff in the PowerPoint as well. So I'll just update that when we get there. And then we've got our assignment for today. Any questions before we go forward? All right, let's do it. Okay, so we're looking at some other fun graph algorithms. One of the things that we haven't talked about so much is planarity. So planarity, in its very simple definition, is making sure that lines don't cross. So we can have something like the butterfly graph over here, or the complete graph K4, where we can draw it in a way that the lines don't cross each other. Note that that isn't always true. So like for K4, if we draw the vertices like this, and then every vertex is adjacent to every other, so we can draw it in a way that the lines can cross, but we can also draw it in a way that the lines don't cross. So these, when we can draw it so that they don't cross, it's planar. When we can't draw it so that they don't cross, the graph is non-planar. So we spent some time at the beginning looking at the utility graph. And there's also the complete graph K5. These two are famously non-planar. So we can't draw them that way. So yeah, so depending on how you draw it, if it can be planar, then we say that the graph is planar as a whole. So even though if we draw K4 in a non-planar way, we could have drawn it where you like take this edge and like pull it out. So it's outside here. If you can draw it that way, then we say that the graph is planar. So the way that we say that a graph is planar, we have to figure out, can we draw it in a way that no lines cross? And so this algorithm is kind of by construction. So the book doesn't go into very much detail, I suspect because it may be more complicated than that, especially because of this step to find a Hamiltonian cycle. Because finding a Hamiltonian cycle is NP-complete. But we can do our best guess. So we can, if we're given some graph, first we find this Hamiltonian cycle, and then we draw like just that cycle by itself and have a list of edges off to the side of here's everything else that's not in that cycle. And then what we do is we try and partition those edges into two disjoint sets where some of those edges go inside. So we'll see like if this is the cycle and we've got our list of edges over here. Some of the edges will say go inside and others we say go outside. Where these all will go inside without crossing. So maybe it's like this, but we can't have something that goes like that. And then the outside edges can go, or no, let's say it goes like that. So if we can draw all those outside edges so that it doesn't cross. If we can do that, if we can partition this set of other edges in that way, then it's planar. If as we go, we reach some thing where we cannot draw it like that, then it's not planar. So that's kind of how we do that. So let's look at an example. So this is the one that they have in the book. So this is our graph to start with. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9 vertices and several edges. And so we start with a Hamiltonian cycle. And so that's just going to be A through I all the way around. G, H, I. That one looks better than the one that I drew over here. All right, so these are the ones that's my Hamiltonian cycle, and now I have a list of all of these edges. So we have a C, a D, a E, and a H. So that takes care of all those from A. Then for the ones from B, B, D, B, G, B, I. And then D, E, F, Gs. We've got D, F, E, H, F, H, and G, I. So these are all those edges that we left out of our cycle. And the job is to assign, let's try and draw them in a way so that they don't overlap. This happens in this building. Like I've had a classroom over there where for the second half of the semester, like it was every day someone's like stomping upstairs. But oh well. Okay, so this is proof by construction, so it's kind of trial and error to some extent. So let's start and say AC, and let's draw that inside. So maybe I'll put a letter A or B next to it. So if this is our cycle, we want to put a cycle in A, which is the inside, and B, which is the outside. Okay, so if we put A, E in, then we're disallowed from doing BD. So any of the B's we can't do because that would cross. So all of these, let's put them in B instead. So BD would cross, BG would cross, BI would cross. So we can do BD, BG, and BI. So far, so good. Okay, so let's consider Okay, it says I'm also following the book to make sure that I don't get lost. So the edge BD is compatible with each edge in the list. So BD doesn't interfere with the ones that we have left. AD, we could put that inside. AD we could put inside but not outside. AE is okay. AH is okay. DF, BD doesn't interfere with that. EH, same, and GI, same. So after we add things to one of the sets, we are kind of checking which ones does this conflict with, and if it conflicts, that means it's got to go in the other one. So let's look at BG. If we look at BG, which is the one going all the way around, let's see AD. So again, so yeah, so BG, we couldn't go around for AG, or AD. So it's AD, EH, and FH that causes problems with that one. So we put AD inside. EH, we put inside. And FH we put inside. So we did AD, EH, and FH. And so now we've just got 3 left. So BI, we couldn't do AH outside with that. So AH has got to go inside. So all the A's are done. And then DF can't go inside because that would cross the EH line. So DF should go outside. That's B. And then we've only got one left, GI, and can't go inside because it will cross all 3 of those. So we put it outside. Yeah. Did I draw AE? No, I didn't. Now I have. Luckily, it doesn't cause a problem. Did I forget anything else? Cool. So now that we've separated these into 2 disjoint sets, so some edges in A, some edges in B, and it's like we've pulled out some of the edges to go around. And so once we come up with this planar embedding, then we can see the graph is planar. Hooray. Okay, so now you try. So we've got 2 graphs here, A and B. And so try and figure out if each one is planar. Okay, so A is planar. What about B? No, not planar. Okay, that's what the book says too. So good job. Yeah, and so in the process of doing this, you reach a point where you're like, this edge that I put into one set, it's like it's kind of like dominoes, right? Where if you put this into one set and then this into the other set, and then you'll reach a point where like I have a third thing that I need to put in either one, but both of these mean that I can't put it in either. So that there lies the contradiction. Okay. So I've got other problems for you to think about. So first one is there once was a king with 5 sons, and in his will he stated that after his death, each son should build his own castle And the 5 castles should be connected in pairs by non-intersecting roads. Can the terms of the will be satisfied? We should have an immediate answer. What is the... No? Yeah, so the immediate answer is no. So convince me. Draw the... I've got whiteboard markers if you want to put it on the board. So go through the algorithm and prove to me that we can't do this. Just a draw. Okay, what graph is this? Yeah, K5. Okay. Um, so if we wanted to prove this, it's terrible. Okay, so we've got, let's name them A, B, C, D, E. And so then not pictured are AC, AD, BD, BE. Is that it? Dun, 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 dun. EC. Yeah. Okay, so let's try putting AC inside. AD is also okay. BD is not allowed now, so we put that outside. BE, not allowed inside, so we stick it outside. And then EC, here lies the problem, where we can't go inside and we can't go outside. So poor EC means that the king's sons can't build their castles. Okay. And I just realized that there's text that's going to show up below this. Okay. So what graph is this? We answered that K5. The question here says, for what value of n, so if we're doing Kn, for what values, this should be an S, for what values of n can this be satisfied? No, what, no. So for n equals 5, thumbs down. For n less than 5, talk about it with your neighbor. Okay, I heard a consensus over here.
So if we tried above 5, we just tried 6.
Mhm.
Getting 5 at a point. So
Okay.
we presume it's just one below. 4, 3, 2, 1.
Right. Wait, how did we draw K4? Like this? Yeah. I'm missing one. So yeah, so like we can draw these and see clearly that they are planar. Um, K5 doesn't work. Did you guys check bigger than 5?
6.
Yeah. Okay. So yeah, so maybe n less than or equal to 4, maybe. There's something that I want to make a new slide so we can talk about it. So there's something that the book mentions that I don't want to go into too much detail, but just so that you're aware, there's this theorem by a guy named Kuratowski. And this guy said that if so that a graph is planar if and only if it contains no subdivision of K5 or K33. Subdivision is not the same thing as subgraph. They have some examples where, like, let's say that this is some graph G, and then if we redraw it over here, we can insert vertices of degree 2 to kind of like break up these edges. And that's a subdivision of G. So if we insert vertices like that, the general shape still looks like G. And so we can get that similarly. So if we like have K5, then if we insert vertices along here as we go, then that's a subdivision of K5. And so as long as something like this exists, as long as there's some semblance of K5 or K33, remember K33 is this guy? The complete bipartite graph on 3 and 3 vertices. So as long as we have something like that, then embedded in our graph, then it's impossible for it to be planar. So yeah, so the one that an example that the book gives is something like this. And then if we have, even if we have other things going on in here, so something like this, is there's still this subdivision of K5. And so we can't make it planar. So this proof is super complicated. So we're just stating it and moving on. But that's the thing. So if you see K5 or K33, then you know that it's not planar. Okay, so now I've got an activity for the last, I don't know, half an hour of class. See how long it takes. If you finish early, then great. Um, so first step, if you open up like a Colab Jupyter notebook, I want you to practice creating some random graphs. There's a link here of different generators that you can use. So you can use like you do like a barbell graph or just play with some different things. And first off, generate maybe like, I don't know, 2 or 3. Let's say 3 random graphs and run through the algorithm by hand and ask if they're planar. And then what you can do is if you go to like draw the graph, then you can also ask like, is this graph planar? So I have an example here. I would like to sign in. Okay. So I was just testing this earlier. I've got this connected caveman graph. And so I would generate this graph and then by hand try and figure out, draw those edges, separate them, and is it planar? And then you can verify that with the option to draw the planar layout. And so if we do that and give it a second to run, and then it can draw it, if it's planar, then it can draw it like that for us. But I believe so what's the caveman graph give us? L cliques of size K. So if I give it some thing that I know is not planar, then it'll raise an exception. But if it is planar, then we can't draw it like that. As you go through, if you see like some term here that you don't know, you can ask or Google it. So like cliques is just it's another way to say like a complete subgraph. So like the clique in here, if we draw it not planar, and next up draw G, just without doing that. The clique is the complete subgraph. So like 1, 2, 3, 4, 5. Wait, I don't think. Hold on. K55 isn't planar. I think it's the way they connect them. Okay, so that's your first task. To generate 3 random graphs, do it by hand, and then draw it and test if it's planar. So do that. I'll give maybe, depending how long it takes, 5-10 minutes. And then we'll come back and do more. So I'll let you keep working on that. I want to add in another activity that you can spend the class time working on. So one of them is the 9-hole golf course, where if we had something like, let's see, the book has this drawing where they like, if this is 1 and then this connects to fairway 2, and then it like crosses. And then goes back to fairway 1. Like if it crosses like this, then I don't know, could be dangerous if we've got golf balls flying across the paths. So generate some kind of graph. So I think the one the book says implies that it's a cycle. Does anyone here actually play golf? No? Okay. Well, I was hoping. Because I think the idea is like you do all this and then you go back to the first one. Um, so can we draw this sort of graph where there's a sequential numbering? And so maybe you can draw it like this, where you go and go back around to the start. And then there's the highway problem where, like, let's see an example. Um, let me pull up the map. So maybe we're in this sort of situation where highways, they have interchanges where 680 is going south and then it turns to continue going south-ish. But 24 splits off of that. And then there's all these intersections where like these highways are crossing these highways, where like this is the Ignacio Valley Road exit, but it's above the lanes of 680 going south and north. So the question here is, given some non-planar graph, let's maybe assume it's a highway system. How can we choose, first, how do you figure out the number of interchanges? And then second, if we've got this non-planar graph, can we minimize the number of interchanges? And so give an algorithm to do so that's either come up with your own or adapt one that we have. And then the third aspect is, so I've given you the golf course and the highways. So come up with your own application. And so write it in like the text cell. This is my application. And then come up with some graph and solve it. Sounds good? Well, feel free to work with your neighbors and work together. If you want to turn in only one notebook, that's fine. And just write in comments, here's who I worked with. So collaborate, work together, have fun.